in this video I will make plate analysis and design. Now since y is the vertical axis and my plate is lies in a floor plane, if we think a building as a structure, that's why I want to replace this grid system in the XZ plane. Click edit here, change the plane of the grid system, and then click OK. Now I want to create a plate, but I want to create the plate is actually the floor in my building, but I will not create here the whole building. I will create here the floor, but I want to create a floor with beams, at least with edge beams. As a result, I want to draw beams. Now let's draw our beams. 5 meter, 3 meters. Finished. Beams are drawn. Now I want to create my plate. Let's create our plate. We can create plate using different options or commands. Okay, plate is also created. Let's divide this plate and the surrounding edge beams into sub-elements. Means that generate plate mesh, quadrilateral meshing I will use. Number of division. These are the lengths of the edges of the plate. Number of divisions. I think here is AB. Let's make here 5 divisions. And to CD, let's make 5 divisions. And along BC and DA, I want 3 divisions. As a result, I want all beam elements and plate elements composed of 1 meter edge. Apply. Okay. We have created them. My beams are also divided into segments because it should have been so that the connectivity between beam and plate elements happens at the nodes, at the common nodes. So we have to make the nodes of the beam and plate elements common, so that the finite element method works. Okay, let's from general menu create support. I want pinned supports, or let's use fixed supports. Click add. Use cursor to assign. Cursor to assign. I want different support type along those edges. Click OK. And then now define beam. That's okay. Concrete. Okay. And then click that one. Okay. Now assign this property together with its this section together with its material to the beam elements. Okay. Now assign plate thickness and its material to plate elements. Now load and definitions. We must define a load. Let's add a load. Primary load. I will loading type no. Title load case 1. That's okay. I will do just only one load. No combination, no second load. And add some loads to that, to this primary load. Okay, let's add the subweight. Let's add floor load to the beams. Go y direction minus 5 kilonewton per square meter. Actually, this is floor load. It is a pressure. Floor load is a pressure, acts on the floor. But it is distributed, it's calculated and converted to some trapezoidal member load and acted on the beams, as far as I know. And its y range is 0. Click on add. That's also on plate loads. Let's apply another load. Let's make it 10. Direction is local z. Local z, as you see, is the axis, local plate axis, which is perpendicular to the plate plane. But I prefer use global y-axis and put here negative sign. And click on add. Okay. Now, self-weight. I want to assign self-weight to the all members, plate elements and also beam elements. Assign to the floor load. As you see, floor load is already assigned because of its definition at floor level. As you see, floor load, for example, for this beam is calculated from the floor area or the flap area as a triangular uniform member load and acted to the beam. As you see, here the distribution or the shading goes to the beams are calculated on the floor plane and then distributed and acted to the beams. So floor load, from my understanding, acts upon beams. This is pressure load. It has to be assigned to selected place. So for that reason, I will select plates and assign to the selected place. Assign. Now they are all assigned. Now, as you see here, when I click on this, the active selected load is shown with blue color. If I click on this, active selected load is shown with blue color. For self-weight, we don't see anything. That's okay. So our loads are also assigned to our structure, and now load center analysis. In the analysis, okay, that's okay. Analysis has finished. Now we can see analysis results. What are the analysis results in the post-processing plane for load case 1? Let's see the analysis results. As you know, from here we see the node results, coordinates or node displacements, and beam relative displacements we see here. Plate results, sorry, come here, not displacements, and reactions developed at the node. We can carry those writings and to make them easily readable, and then using print screen or on the keyboard we can take the pictures to get the visual information about the support forces and moments, or we can take a picture and then copy pic. Sorry. After taking the picture, so take a picture, I have to copy the picture to paste here. That's one way. We can see reactions and displacements. We can see also displacements by clicking to here and then pressing on control button and playing with the scroll button of the mouse. We can see some beam stresses, plate stresses, bending. Well, these are for beam elements. We can see results for beam elements and for plate elements separately. Here we see reactions and displacements. From the results menu, we can select view value, nodal displacements, for example in global Z, annotations can be written here. From here we can read the vertical displacement values at the nodes, or the resultant we can read, remove all, and there are some other possibilities. Information about displacements are also provided at the tables given at the right hand side. For beams, beam end forces are given here. These are not beam internal forces, they are beam end forces. Internal forces are given here. Beam internal forces are given here. You can also see we have only at the edge beams. This slab or the floor is a let's say plate element, slab or floor, which has only edge beams. We can see axial force. We can play with scroll, pressing on control button in the keyboard. We can see the variation of normal force in the beams, shear force, let's close this, and another shear force in the Z direction, and torsion. So what is this? I can see FC. I think it's very small in comparison to Fy. We can see torsion developed in some beams. Bending moment. This bending moment is small. Okay, another bending moment. Keep in mind that those forces are according to the elements. Now here the elements are the beams with respect to the local coordinates of the beams. We can see the beam stress. But actually it's stupid to see here beam stress. Beam compression and tension stresses are given here on the diagram. Actually we don't see their values, but we see their variations. So we can understand which beam is enforced very much in comparison to the others, and this is for plate stresses. Now for plate elements, we encounter with this table. We have just plate stress counters. We will watch with this table. If I say no and click on here, I will encounter with the same table. We will use this table to see the stresses, moments developed on the plate elements. Now we can from here select some stresses or internal forces. The contour type can be selected from here, and though we can change some options from here. This is the here we will see some values about the variable what we select here. We see its values, variation of this item in this table and then in the plate as a two-dimensional diagram. Now first of all I want to look to the definition of plate stresses. Okay. Element stresses may be obtained at the center and at the joints of the solid element. The items are printed here. But this is for solid element. But I think this is also valid for plate element. These are normal stresses. SXX, XYY, XZZ. We can also look here to see to see them. Let's look here now from now at the current moment. Forget this here. Let's come here. Now sign conventions for plate stresses and moments, top surface and bottom surface. Now we have SX, SY, SXY forces. These are forces. And those forces are membrane forces. Okay, membrane forces. We have moments. We have forces here. These are shear forces. SQX, XQX, XQY. Okay. And we have bending moments. MX, XO, MY, XO, and torsion moments. Torsion moments are shown with those arrows. Now for MX and MY, MX acts along the edge of a plate element as shown here and as shown here, and Y acts to the edge of the plate element as shown here. Okay. Now stress caused by MX. This is the stress caused by MX. As you see, it is like MX, the bending moment developed in a beam, and these are the bending moment normal stresses. and the stress is caused by my. As you understand, at the here is the neutral axis or the neutral plane, and the stress value here is 0. Okay? Or if you integrate this stress along the thickness of the plate, you will get 0 stress, because this value equals to this value and they cancel each other because they have opposite signs. But the stress distribution because of mx is so. And because of my is so. Okay. And the stress distribution because of torsional mxy and myx is not shown here. Actually, it should be something like that. Something like that. That's okay. 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 Now we have investigated stresses induced by mx, mx, my, and myx or mxy. That's okay. That's okay. That's okay. Now, because of shear forces SQX and SQY, the shear stresses developed at the plate X as shown here. So that's also illustrated. We have, in addition to, those are forces, not stresses. Those are also forces. Because of those forces, S X and XY, we have those stresses, membrane stresses. Tensile, or if negative, they are compressive. And they are uniformly distributed along the thickness of the plate. And that's the in-plane shear force, and its distribution is given here. Okay? So those are the symbols of forces, plate forces. So we can see those forces, variation of those forces. Let's see the variation of those forces. Here it's written stress, but we can see also forces, not stress. Sx is a force. Okay. Sx, Sy, Sxy. Okay, they are forces. Apply. We have no xy force. They are provided, those stresses are provided in terms of local plate axis. You know, local axes are in plane x, y axis, and perpendicular to plate plane, we have local z axis. And those forces, internal forces, are always provided by the program in terms of local axis. Fy 0, fxy 0, mx bending moment, it's non-zero. You see the variation, okay? You see minus 3.2, minus 2.84, minus 3.2, minus 3.84. Here, the range is given here, okay? Okay, so this color has the top and bottom limit values. So maximum bending moment develops, negative maximum bending moments develops at those fixed edges, plate edges. Okay, and at the span mint we have positive bending moments, as you see here. Okay, what's its unit? Kilonewton meter per meter. We can also see my values. My has higher value. Torsion, plate torsion. It's small. And SQX is like SQY. They are plate shear forces, but they are out of plane, not in plane, unlike SXY. They are small. We have then, did we check? Yeah, we have checked them. Membrane SX, SY, and SXY forces. SXY in plane shear, it was also almost zero. It's almost zero. Because of the symmetry of the geometry and the loading of the structure, it's normal that this has the result zero value. Now those values, try to understand what those values are. Top combined, top combined, top combined. So what could be those values? We have a normal stress because of Sx, and we have a normal stress because of Mx. So if you combine those at top, normal stress value in the x direction would be higher. If you combine those at the bottom, since this has an opposite sign in comparison to that, at the bottom we have a lower value. So they are combined, same type of stresses are combined. For example, because of Sx and Mx, we have combined Sx. Now Sx is actually Sxx. There should be two x here. Okay, it's false written here SS. It should be SSX at the top of the plate. And it's the normal combined normal stress. Let's check its value. At the top, so much. Sy at the top, and its value is given in terms of megapascal. Now look, now it's not force, it's a stress, and its unit is megapascal. Top Sxy was already small. XY stresses develop because of let's where is it? Because of torsion and because of in plane, because of that and because of that. Okay. Now at the bottom, that's okay. So these are some special norms, calculate stress functions, calculated as a function of sx, x, y, and blah blah blah. You can find their definitions. Generally, von Mises stress is checked. Von Mises stress is checked. We can check von Mises stress at top and bottom. And generally, what is done in engineering offices is check the von Mises stress, which is a function of all other stresses, and compare it with the yield stress or the yield strength of the now here plate material. It has a very low value. Okay. Top and bottom I check. And maximum value of von Mises stress. The value of von Mises stress is always positive. Positive. And principal stresses, principal stresses from strength of materials, what is, the definition of principal stresses. I will not explain them here. Principal stress values, they are also important. Top and bottom. And among those were the important and what I have understood. What is tau? Is there any explanation for tau? Tau is tau can be tau. Tau is the symbol used for shear stress. Shear stress, but stress. But here shear stresses are given generally with those symbols, not with tau for plate elements. Now here we have for normal stresses are here, but for shear stresses, maybe I couldn't find it in the top combined as xy. SXY is because of SXY is because of that force and that force. So tau, okay, tau is the stress caused induced by those forces, as I guess. Okay. That's the stress values, which has physical explanations according to those drawings, and which I found useful to explain and to check the results. Uh, okay, we can also select this option and see the differences between. I think normal fill is the better. Okay. That's how we see plate internal forces and stresses. Results along line is also possible. I think someone draws a line and see the value of stresses along this line. I didn't work on this. I don't know how to do this. You can make also animation. You can animate deflection and section displacement. Let's make the animation of deflection. Let's make the animation of section displacement. Now in the deflection, we see that. If we say section displacement, we see the beam's deflections are also seen. I think the section displacement is the thing what we seek, but deflection is something else. And we can obtain the result, reports also from here. To obtain results I have shown before. I will not do it now for plate element. Let's say cancel. And in the model page, let's continue it. Can I learn the difference between deflection and displacement? Okay, what we know. Deflection is the distance from the line that links the origin and at nodes of the bar on the deformed model with the position of point on the deformed model. Didn't understand. Global displacement in the y direction. I think this is not for step. Okay, don't waste time with those things. I have wasted a lot of time. Now we will make design of plate. To make the design of plate, we will select parameters. But we have to select concrete tab, select parameters. I will make the design on the plate elements, not beam elements. Only for bottom reinforcement, cover, compressive force of concrete, and only yield strength for the main reinforcement. Okay, define parameters. Design slab element. I want to assign to selected beam plates. I want to assign those values only to plate elements. I want to assign this value also to only to plate elements. Again, okay. Design elements also. Okay, let's make analysis. You can make analysis from here. Make linear analysis. Analyze, run analysis. View output file. We can view output file now, but I will view it later. Geometry. Now my plate elements are here. Here, when I click on them, unlike two beams and columns or frame members, we can see its geometry, information about it, property constants, some stress values about it. Okay, this is toe shear stress, and these are normal stresses, principal stresses. Principal stresses are important. Remember from Mohr circle what principal stress are. Corner stresses, values of corner stresses or the plate selected plate element, and center stresses. Those stresses developed at the center. And as you see, there is a mistake here, I think, because stresses are shown with those symbols. However, those symbols are used for internal moments and internal forces, shear and normal forces. So some things are confused by the program developer. That's my idea. But from here, we can look separately by means of right-clicking on any plate element, slab element, or floor element. We can learn the design, what design was done for that slab element. I mean the reinforcement amount and other things. But we have just one possibility. We will go to the output file. Now in the output file, element design is done as per ACI 318. Start concrete design. For those members, cover at the bottom, clear cover of concrete at the bottom is dead. Concrete strength is dead. Yield strength of rebar is dead, and design those elements. Those elements are starting from 8 plate element and ending with 32 number plate element. Now here, the design result of, as you see here, element number is given in this column. Element 8, plate 8 is given here. But some things are stupid here. Here, these are the captions of the table. But here, for example, longitudinal reinforcement, square millimeter per millimeter. is given here, but we see nothing. Maybe because of this analysis, the results are so. Okay, Fy is given again. Some information is repeated again for every element. And Fc, compressive strength, and cover, clear cover for top. This is calculated, I think, because the cover at the bottom, no, it's not calculated, but I think it's taken anyway. It's a default value maybe. We have defined the clear cover at the bottom. Clear cover at the top was a defined value, default value maybe. The program would put it here. In thickness, okay, 20 centimeter. 8. Element 8. Top longitudinal direction. Only minimum steer required. Top transverse direction. Only minimum steer required. Okay. Bottom longitudinal direction. Only minimum steer required. Bottom transverse direction. Only minimum steer required. So, these are explanations. All those. I can click on that. That's explanation, that's explanation, that's all explanation. So those caption number, those caption or column column names given here belongs to those. So at the top, in the long direction, we have 0.149 millimeter square or square millimeter per millimeter rebar area. Okay, and at the top, and mx is 0. mx is 0. mx caused by which load? 0 load. So there is no load in this direction. I didn't understand. I have defined just one load. That's load. mx slash load. That should be load number. So mx is 0. That's 0. In the transverse direction at the top. So at the top, in the longitudinal direction, the rebar is developed, the rebar is calculated for because of mx bending moment. mx bending moment is 0. This is the minimum reinforcement area. At top, at the transverse direction, we have my. It's induced because of load 1. And again, the required area is that. Okay. So I think there is a load in every direction because we have just one load and it has the identification number 1. Since this value is 0, program puts 0 value here. I think that should be 1 also. So at the bottom in the longitudinal direction, now, at the bottom, in the longitudinal direction, we have reinforcement area so much, and mx moment value is that because of load 1. In the transverse direction at the bottom, that's the reinforcement area, but moment value my is 0. My is 0. Okay. Now think about it. That are the results provided by the program. Maybe if I have increased the amount of load, the program would have considered more reinforcement area instead of minimum values. Okay, here there are some explanations. You can read them. Element design will be perfect. I'm not sure about that. I have taken this, but it might here it is written for solid elements. Better erase this. Might be not valid for the plate element, only for solid element. Element design. Element design will be performed only for the moments mx and my at the center of the element. Okay. So for plate elements, only bending moments are considered, and only in two directions perpendicular to each other, longitudinal rebars are put in the plate. Design will not be performed for those internal forces and moments. Also, design is not performed at any other points on the surface of the element. Design is performed only according to value of mx and my at the center point of the centroid of the plate element. A typical example of element design output is shown in this table. The reinforcement required to resist mx moment is denoted as longitudinal reinforcement, and the reinforcement required to resist my moment is denoted as transverse reinforcement. Now in this figure, you see this is mx. So sorry, this is mx. This is mx. So this is the longitudinal reinforcement. Okay, of course, the direction of reinforcement should be that one. As you see, that is, where is it? That is my. And in this direction, this reinforcement is formed. Now we have learned this. Okay. Now that's clear. The parameters Fy main is the strength of the rebar. Fc is the strength of the compressive strength of the concrete, and clear is listed in table 3.1. I think this clear is the concrete cover. The parameters, the value of those, concrete cover. You see Fy compressive strength in terms of foot-pound-inch units, clear cover value or concrete cover value at the top and at the bottom. Thickness is the same information we had in our output file. Other parameters mentioned in this table are not applicable to slab design. Please note that the default value of clear cover parameters for plate elements is so much. Okay, default. If we do not define anything for clear cover, the program puts use the value according to the selected concrete standard. We have selected ACI. The result is here similar. Longitudinal direction on the minimum steel cut. Longitudinal direction is this direction of mx. It depends on the local axis of the plate element. Transverse direction is the direction of my. And at the bottom, you see here, if the value is 0, load value appears here as 0. So this second 0 has no importance. So at the top, here at the top, reinforcement, because of mx. So this is the top longitudinal direction. This is the, so mx is, the value of mx is carried here. At the top, in the transverse direction, value of my is kept here. Okay. Okay. Both have 0 values. So minimum minimum reinforcement is put there. At the bottom, they both have values. Now this is more meaningful. They both have values, mx and my. And in the longitudinal and in the transverse direction, mx and my has values, meaningful values, and the reinforcement area differs from the minimum area of zero reinforcement. A good example was that. Without saying anything, let's close it. We made a lot of explanations about slab or plate, slab plate or floor